We are Group 2 and this is a presentation of our ICT activities. In this presentation, we will have an introduction, we will do a demonstration of the activities, we will analyze these activities using the UDL framework, TPAC framework, SMAR framework, and have a conclusion. This lesson is for Grade 8 Natural Science. It is based on the topic of electric circuits. By the end of these activities, learners will be able to predict, observe, and explain how the brightness of a light bulb is affected by adding or removing resistors in both series and parallel circuits. For the first activity, we decided to use a FET simulation. Learners will first be given a worksheet in which they will make predictions of what would happen when adding and removing resistors in series and parallel circuits. Then after, they will use the link sent to them on their electronic devices and log in and do the FET simulation. While doing the FET simulation, learners will add light bulbs in series, add light bulbs in parallel, and note what will happen. They will take note of this on their worksheet. In the next slide. From this, learners will be able to see the effects of adding and removing light bulbs in series and parallel circuits.
After completing the series and parallel circuit investigation, we plan to use Kahoot as an interactive formative assessment tool. The purpose of this activity is to assess learners' application of concepts, not just their recall of definitions. The Kahoot will consist out of 5 questions: 2 multiple choice, 2 true and false, and 1 rearranging question. Learners will join the Kahoot quiz using their electronic devices. Each question will appear on the board, and they will have a short time limit to respond. The questions will focus on applying what they observed in the investigation. Using Kahoot allows for immediate feedback and visual engagement. Learners can see their scores and rankings in real time, which keeps them motivated and encourages friendly competition. As a teacher, we can quickly identify any misconceptions through the answer summaries displayed after each question. This helps us adapt our next lesson to address those problem areas. Overall, this Kahoot activity will act as both a consolidation exercise and an informal assessment tool, helping learners link their practical findings with theoretical understanding in an enjoyable, technology enhanced way.
In this section, I'll explain how the learning activities align with the UDL framework and then evaluate how effectively UDL principles were integrated. This lesson on electric circuits uses 3 main activities: a FET simulation, a written worksheet, and a Kahoot quiz, which together address the 3 UDL principles: representation, action and expression, and engagement. For representation, content is presented in multiple ways as the learners use the FET simulation to visualize current voltage and resistance, while circuit diagrams, symbols, and real life analogies help connect abstract ideas to prior knowledge. For action and expression, learners build and test circuits, record their findings in the Predict, Observe, Explain worksheet, and demonstrate understanding through the Kahoot quiz. These options let learners express what they know in both written and digital forms. For engagement, both tools make learning interactive and enjoyable, as the simulation encourages curiosity and experimentation, while Kahoot adds a fun, competitive element that maintains motivation and provides instant feedback. In terms of critical evaluation, the UDL integration is strong but could be improved. The visual focus of the simulation might challenge learners who benefit more from verbal explanations, and the fast pace of Kahoot could affect deeper thinking. To address this, I'd add guided reflections after the simulation and include a justification step in Kahoot to promote reasoning. Allowing audio explanations or visual responses alongside the worksheet would further support diverse expression. Overall, these small improvements would enhance inclusivity and ensure all learners can access, engage with, and express their understanding effectively.
This activity, the content knowledge focuses on understanding key concepts of electric circuits, especially the difference between series and parallel arrangements and their effect on bulb brightness. Learners explore how circuit structure influences current and voltage. In a series circuit, current remains constant while voltage is shared, whereas in a parallel circuit, voltage stays the same across branches and current divides according to resistance. They also examine brightness as an indicator of energy transfer. Bulbs in series dim as more are added, while bulbs in parallel maintain brightness due to equal voltage. Finally, learners apply their understanding of circuit diagrams and symbols by constructing accurate real or simulated circuits, building a solid foundation for analyzing electrical systems. Of this content is facilitated through interactive and student-centered activities that promote conceptual understanding and active engagement. Using the PET simulation, learners can construct and manipulate both series and parallel circuits in a virtual environment, allowing them to observe how changes in circuit structure affect current voltage and bulb brightness. This hands-on exploration helps make invisible electrical processes visible, as students can directly measure current and voltage using virtual instruments while noticing the resulting differences in brightness. Through guided inquiry, they develop a deeper understanding of energy transfer and the relationships between circuit components. To reinforce learning, a Kahoot quiz is used to consolidate knowledge through retrieval practice and formative assessment. This activity not only checks learners' understanding and addresses misconceptions, but also strengthens the use of key terminology such as series, parallel, current, and voltage. Together, these tools can create an engaging and multimodal learning experience that connects theory with practice and fosters meaningful understanding of electrical circuits. Logical knowledge in this activity is rooted in an inquiry-based, student-centered approach that promotes active engagement and conceptual understanding. Learners use the PET simulation to design, modify, and test circuits following a predict, observe, explain cycle that encourages them to make hypotheses, observe outcomes such as bulb brightness and current readings, and explain their reasoning. This process not only fosters critical thinking but also helps uncover and correct misconceptions, such as the common belief that current is used up. Through guided inquiry and multiple representations, abstract concepts like current, voltage, and resistance become more concrete. The teacher scaffolds learning by linking visual simulations with real-life analogies, formal circuit diagrams, and observable phenomena, enabling students to connect prior knowledge with new scientific ideas. Learning is further enhanced through collaboration, where students work in pairs or small groups to share observations and discuss interpretations. The inclusion of interactive formative assessments using Kahoot provides immediate feedback and reinforces key concepts, while differentiation ensures that diverse learning needs are met. Finally, reflection and consolidation activities encourage learners to relate what they have learned to everyday electrical systems, solidifying both conceptual and practical understanding. Technological knowledge involves the teacher's ability to select and integrate digital tools that enhance both the understanding of content such as series and parallel circuits and the concept of brightness, and the effectiveness of pedagogy through exploration, inquiry, feedback, and assessment. The use of a PET simulation makes invisible processes like current flow and voltage variation visible, supporting inquiry-based learning by allowing students to conduct unlimited, safe experiments beyond the constraints of a physical lab. It also promotes differentiated learning as tasks can be scaffolded to meet varying levels of student ability, and its online accessibility extends learning opportunities beyond the classroom. Complementing this, the use of a Kahoot quiz transforms assessment into engaging and interactive experience, providing immediate feedback on conceptual understanding. It boosts learner motivation, caters to diverse learning styles, and offers teachers real-time data to quickly identify and address misconceptions. In this lesson, the teacher demonstrates a strong CK by accurately explaining series and parallel circuits, focusing on how current, voltage, and brightness of bulbs relate, while addressing common misconceptions such as the idea that current is used up. Through PK, the teacher employs inquiry-based learning, scaffolding tasks from simple to complex circuit designs, and using questioning and peer discussions as formative assessment to support conceptual growth. The integration of TK enhances learning through tools like PET simulations, which make invisible processes such as current flow visible, and Kahoot quizzes, which gamify assessment and provide instant feedback to maintain learner motivation. By combining TCK, the PET simulation translates abstract circuit concepts into visual interactive experience that clarify how changes in series or parallel arrangements affect the system. Through PCK, the teacher sequences topics thoughtfully and uses analogies to explain current and voltage distribution effectively. The use of TPK transforms assessment into an interactive and engaging process using Kahoot, allowing misconceptions to be identified and addressed immediately. Ultimately, when content pedagogy and technology intersect through technological pedagogical content knowledge TPEC, they create a cohesive student-centered learning environment where technology enriches pedagogy, makes content more accessible, and deepens learners' conceptual understanding.
For the main part of our lesson, we use the PET simulation, which is a clear example of modification. The main idea of modification is that the core activity is changed. In a traditional class, the core activity would be building a physical circuit and observing a single specific outcome. The main focus there is on procedure and construction. The PET simulation changes this core activity completely. It's instant, risk-free, and allows students to actively experiment with what-if scenarios and see abstract concepts like electron flow. This redesigns the task, shifting the focus from just building the circuit to actually understanding the principles behind it. We then explored how to push this even further into real definition. The new task is for students to use the simulation to explain a real-world device, that being a power bank. They would first have to model the charging phase, showing energy being stored in a battery, and then the using phase, where the battery powers a light bulb, representing a phone. The activity is classified as redefinition because the task changes completely from a single lab into a complex challenge, where students must create a scientific model to explain a real-world technology. This new task would have been much more difficult to do in a traditional classroom. For our consolidation exercise, we are using a Kahoot quiz which we've classified as augmentation. At its most basic level, Kahoot is a substitute for a regular paper quiz, but it becomes augmentation because of the three key functional improvements. It boosts student engagement through points and competition, it provides immediate feedback to reinforce concepts, and it gives the teacher efficient data to see where the students are struggling. However, we saw an opportunity for deeper tech integration. The problem with any multiple choice quiz is that students can simply guess the right answer. To solve this, we will push this activity to modification. After each question, we will add a justification tab where students must type a short sentence explaining why they chose their answer. This simple step fundamentally changes the core task from basic selection to active critical thinking. By redesigning this activity to focus on student reasoning, we elevate the use of technology to the modification level.
In conclusion, our activity effectively demonstrates the TPACK framework by using a PhET simulation for discovery and a Kahoot quiz for assessment. This approach aligns with the UDL principles by offering multiple ways for students to engage and express their learning. By moving beyond simple substitution on the SAMR model, our activity makes abstract circuit concepts visible and creates a more dynamic learning experience.